The speed of light in vacuum is a universal physical constant exactly equal to 186,000 miles per second or 671 million miles per hour. It is exact because the international agreement, the speed of light is the same for all observers, no matter their relative velocity. It is the upper limit for speed at which information, matter, and energy can travel through space. All forms of electromagnetic radiation, including visible light, travel at the speed of light. For many practical purposes, light and other electromagnetic waves will appear to propagate instantaneously, but for long distances and sensitive measurements, their finite speed has noticeable effects. Many starlights viewed on Earth are from distant planets, allowing humans to study the history of the universe by viewing the distant objects. When communicating with distant space probes, it takes hours for the signal to travel. In computing, the speed of light fixes the ultimate minimum communication delay. The speed of light can be used in the time of flight measurements to measure large distances to extremely high precision. Ali Romer first demonstrated that the light does not travel instantaneously by studying the apparent motion of Jupiter's moon Io. In an 1865 paper, James Clerk Maxwell proposed that light was an electromagnetic wave and therefore traveled at the speed of light in a vacuum. Albert Einstein postulated that the speed of light in a vacuum with respect to any internal frame of reference is a constant and is independent of the motion of the light source. He explored the consequences of that postulate by deriving the theory of relativity, and so showed that the parameter speed of light in a vacuum had relevance outside of the context of light and the electromagnetism. Massless particles and field perturbations, such as gravitational waves, also travel at the speed of light in a vacuum. Such particles and waves travel at the speed of light regardless of the motion of the source or the inertial reference frame of the observer. Particles with non-zero rest mass can be accelerated to approach the speed of light in a vacuum but can never reach it. Regardless of the frame of reference in which their speed is measured, in the theory of relativity, the speed of light in a vacuum interrelates space and time and appears in the famous mass-energy equivalence of E equals mc squared. In some cases, objects or waves may appear to travel faster than light. The expansion of the universe is understood to exceed the speed of light beyond a certain boundary. The speed at which light propagates through transparent materials, such as glass or air, is less than the speed of light. Similarly, the speed of electromagnetic waves in the wire cables is slower than the speed of light. The ratio between the speed of light and the speed velocity at which light travels in a material is called the refractive index. For example, for visible light, the refractive index of glass is typically around 1.5, meaning the light in glass travels at the speed of light times 1.5 or at 124,000 miles per second. The refractive index of air for visible light is about 1.0003, so the speed of light in air is about 56 miles per second slower than the speed of light in a vacuum. There are situations in which it may seem that matter, energy, or information carrying signal travels at a speed greater than the speed of light, but they do not. The phase velocity of X-rays through most glasses can routinely exceed the speed of light, but phase velocity does not determine the velocity at which waves convey information. If a laser beam is swept quickly across a distant object, the spot of light can move faster than the speed of light, although the initial movement of spot is delayed because of the time it takes the light to get to the distant objects at the speed of light. However, the only physical entities that are moving are the laser and its emitted light, which travels at the speed of light from the laser to the various positions on the spot. Similarly, a shadow projected onto a distant object can be made to move faster than the speed of light after the delay in time. In neither case, matter, energy, or information does not travel faster than light. In science fiction, people often find a way to move at the speed of light, but you might find yourself asking, could your body survive going so fast? What would happen to it? First, let's assume that it's possible, even though that is not. For a human to move at the speed of light, which is 983,571,156 feet per second, or about 186,000 miles per second. There's no issue, per se, with a person moving at a very fast constant speed. Humans can't feel constant speed, so you wouldn't even necessarily notice you are moving that fast. Your biggest issue would be acceleration, actually reaching that speed. Too much acceleration force can hurt and even kill us. At high accelerations, your blood will have a hard time pumping through the extremities. Most humans can handle acceleration forces of about 4 to 6 times that of gravity, which is 4 to 6 Gs, for a short period of time. As G forces increases, your body's ability to circulate your blood from the feet to your head becomes limited. As your blood begins to pool, you will pass out, and if the force doesn't lessen or stop, you will eventually die as your body is starved of oxygen your blood transports throughout your body. Fighter pilots and other people who experience high levels of G forces are taught techniques to keep from passing out, such as tensing muscles in their extremities and use special suits to withstand up to 9 Gs for short periods of time. But if you were accelerating at the speed of light for a few seconds, like in Star Wars movies or Star Trek, you would quickly become a human pancake as the force of 6,000 Gs slammed into you, according to the Omni calculator's G-force calculator. If you wanted to accelerate more safely, say at 2 Gs, it would take over 5 months to accelerate to light speed. Assuming you are moving in a straight line and there is no air resistance. At 1 G acceleration of a free fall, it would take 11 months. Unfortunately, reaching this lofty speed turns out to be impossible. You cannot go at the speed of light given that you have a finite mass. Einstein's theory of special relativity shows that as an object with mass gets closer to the speed of light, the mass starts to increase as it nears the speed of light, Provincia said. If an object could reach the speed of light, it would become infinitely massive and would require infinite energy to maintain speed. Still, humans have gotten some things to go very, very fast, if you can call a subatomic particle things. Particle accelerators can get particles like electrons to move to over 99.9% of the speed of light, Provincia said. But there's a big difference between getting an electron to move that fast and launching a person at that speed, which would require so much energy as it would be extremely improbable, even if it didn't break the laws of physics. If you could move at near light speed, you would experience the effects of relativity on time, Provincia said. Time will move more slowly for you than other people moving through their everyday speeds, though the experience of time wouldn't change. If you could observe people moving at a normal speed, Provincia said, they would appear to be moving in slow motion. There is one instance in which we would move closer to the speed of light. For example, our planet and everything in the universe are constantly moving. Earth is rotating and revolving around the sun. The sun is rotating around the galaxy. Our galaxy is in motion, and it's possible that we are moving away from our galaxy very quickly. That galaxy is also moving away from us. We would be moving relatively to that galaxy at a near speed of light. So if all speeds are constant, it would be possible that we are already traveling through space at close to the speed of light in a vacuum. I hope you enjoyed this video. Don't forget to like, subscribe, share, and hit that notification icon for the latest videos as they are released. Thanks for watching and catch you in the next one. Ciao for now.